to his job. Welcome to the Bucky Call for the weekend of March 22nd, 23rd, depending on which continent you're on. We're working on Amy Edmondson's book, A Fuller Explanation, and we're going to talk more about spheres today. So great. So, John, it's good to have you on the call. How are you feeling, and what do you anticipate to get out today?
Well, I'm feeling great. It's a beautiful day here. We're just going to have some unseasonably hot weather over the next week, unfortunately. 36 is not what you want in autumn. But anyway, yeah, I feel very fortunate to be alive and to live in Perth, and I feel significant concern for a lot of the rest of the world. But I'm working on becoming more committed to believing that there is always gold in the wound if you look for it. So the planet's certainly being wounded at the moment in lots of places, in lots of ways. But yes, excited at being assisted in my understanding of Bucky and hoping to go out of today with a greater understanding that something that's going to be important to me in the near future. So, Anne, how do you feel? What do you hope to take out of today?
Grateful, very, very grateful. I want to thank Steve for anchoring this for so long now. For both the Wednesday and the weekend meetings. Yeah, very, very grateful. Just want to put it out there. Also, for Amy Edmondson, what she's doing here, because by coming from a very more with the intention of making it accessible for people who may not understand Bucky's language, I'm getting a lot out of this. Yeah, so I'm looking forward to what else we can get from here, from our group, and forever grateful to the two groups that we have on a weekly basis. Then a little bit of an update as well. We just did our TEDx talk in our school yesterday. Little kids, 7 years old, 8 years old, 9 years old, they were speaking, and it blew everybody away. So the minute we're going to be curating and sending it over to TEDx, and then when they put them up on YouTube, I will definitely inform all of you. Okay, I'll send it to you. And one more thing is, I'll be in your neck of the woods time zone. Okay, Steve, Susan, and who else is on that side of time zone?
Richard.
And Richard. Richard, same time zone? Okay, great. So on the 4th until the about 15th. So I'll see what the events are on. And the minute I can, I'll let you know which ones I cannot, our meetings I can't join, but I'll have to go through the scheduling. Okay.
Where will you be?
Vancouver.
Oh, right. Okay.
So yeah, I'll probably have to check in with you on our group chat, because I'm spending about 2 days, at the foothills of Grouse Mountain, that sort of thing. So I'll check in with you. Okay, Richard? Yeah, so very excited about that. And yes, Richard, how do you feel, and what would you like to take away today?
Well, I feel pretty good, but I also feel like I'm kind of running away from you, because I had originally thought if you were in Vancouver in April that I might be wanting to visit our daughter, who's in Chilliwack, only an hour or so away from Vancouver. But when you arrive, we're heading for Ireland. So we're going to be gone for 2 weeks in the first part of April. We're out on a ancestry hunt for the ancestors on my father's side. And with Ramsay, the name, I always have understood that we were Scottish people. But I had an aunt years ago that I always used to interrupt those discussions and say to the family that you're all wrong, we're Irish. And that sort of cut to the core. But now we're starting to realize that a great-grandfather probably was from Ireland, and we're also trying to figure out when his kind of Scottish clan or group came over to Ireland, and so it's all kind of exciting to discover sort of a part of our heritage that has been sort of sitting there covered up by the lack of data or the lack of ships records and all those kinds of things. So yeah, that'll be interesting. And yeah, so I always feel good about reading and dialoguing more about Amy Edmondson's work. John and I actually, when we think back on it, we were in San Diego at the same time in 1995 for the 100th anniversary of Bucky's 100th
100th
birthday
anniversary.
celebration, centennial. I went to a workshop by Amy that she was, it was like an adult workshop. You would have loved it, Anne, because she was trying to get the adults to get back into their childhood and be willing to play with gumdrops and toothpicks to create geometric models. And it took a while for the adults to sort of relax into the playful sort of instruction that she was giving. And once that happened, then I think everybody was delighted with the way she approached things and the way she helped us understand the basics of geometric thinking. So yeah, this is really quite a good connection to have all of us together. And so I'm looking forward to the continued dialogue. And Steve, how are you feeling, and what's your takeaway? What's your interest?
I'm excited to be here. I'm not clear exactly where we left off last time. I think I know where it was. So we'll pursue that in a second. This work with Amy has been exciting because I've actually had a couple of epiphanies, things that should have been obvious that I didn't get before that she clarifies. And then things that I thought I understood, I don't understand. She keeps going further. So it's enlightening to me. I'm really big on energy and how it works, and I look forward to discovering whatever it is we're going to have today. So I'm going to look forward. Now, we left off, for my understanding, we left on page 122. Does that ring a bell for you, Richard?
Yeah, I think so. I was
Yeah.
just wondering whether we had actually, I guess we hadn't finished that chapter, but
Yeah, I think you ended up, the last line was, "This is the shape of space." And then we were about to begin this next thing, I do believe.
I think
What's that?
I'm thinking if we've gone forward another 2 paragraphs, I have a feeling.
Okay, but this was last week. Were you on the call
Yeah.
last week?
But it's okay. I was in the call. But you know what? I think it's good to, because I highlighted this is the shape of space. Let's maybe read. Let's, even whether we've gone forward or not, let's just read from there. I really
Yeah.
I'm very interested. Yeah.
We may
Okay.
have gone forward, but that's what I got when
Yep.
I listened to the recording. So, but I wasn't clear because I didn't see any other pages pop forth. So we'll start there. And let's see here. So there it is. This is the shape of space. Let me see if I can get it a little bit bigger and less is that readable for everybody?
Yes, yes.
Good. We'll do this and this. Now, I don't know if you're up to it, John, you want to read?
Of course I am. Yes, of course.
All right, good, wonderful.
Happy to. Okay. This is the shape of space. It is interesting to note that, although when we stacked triangulated layers, it was necessary to make a decision at the 3rd layer that led to 2 different packings, if we were to start out instead with the square layers, unstable though they may be, there is only one way to proceed, Successive square layers can be placed on top of each other so that each ball lands in a square nest, as opposed to being placed directly on top of another ball, creating an array of cubes which would clearly not be close packed. The internesting of layers stabilizes the otherwise unstable separate layers. Once two layers are packed together, every ball nests in a group of 4 balls on the adjacent layer, creating 1/2 octahedral pyramids, figure 8.6, separated by the inevitable byproduct.
Sorry. Oh my gosh, my cursor's going wacko here. Let's see if I can get this on. Okay, there we go.
Whoa.
Okay.
Stop. The inevitable byproduct, tetrahedra. Continuing to stack square layers in this way, cubic packing, rather than hexagonal, emerges. The vector equilibrium array is thus generated automatically, with no decisions along the way, by simply stacking square layers. Each and every ball is surrounded by exactly 12 others in the more symmetrical of the two possibilities.
Okay, and I'm going to see if I can get this. There we go.
5 oranges stacked to form a half octahedron. It is satisfying to reflect on the exquisite logic of this trade-off. Although balls arranged in square patterns are not as closely packed as triangular planes, the nests are deeper. A ball placed in any 4-ball nest
That should be it. It should be there, John.
Okay. To start, a second layer sinks deeply into the cluster. In comparison, it seems perched on top of the tight triangular nest. Therefore, successive square layers, although inefficient in themselves, fit more closely together than triangulated layers, tetrahedral and octahedral closest sphere packing clusters. Part of the challenge to mathematicians in proving that the hexagonal and cubic packings qualify as the solution to minimizing interstitial space is the fact that spheres in these two packings occupy just over 74% of the available space, while the 4-ball tetrahedron alone is able to occupy 77.96 of its overall volume. It is easy to accept that 4 balls cannot be pushed any closer together than the tetrahedral cluster, and accordingly that the latter figure is the maximum density. Therefore, 74% seems insufficient, not easy to accept as the solution to the problem of closest packing. However, there is no getting around the fact that the 6-ball octahedral cluster is less dense than the 4-ball tetrahedron, as the former has more leftover room in the middle, and that the constraints of space are such that tetrahedral sphere clusters simply cannot be extended indefinitely by themselves. Attempting to fill space exclusively with tetrahedral groups, we quickly discover awkward leftover gaps, spaces not quite big enough to contain another sphere. In order for spheres to be both consistently tangent and tightly nested together, we have to allow the naturally alternating tetrahedral and octahedral clusters. The problem would be remarkably easy if spheres could pack tetrahedrali in an indefinite array, but they cannot. No amount of force can change this constraint. Space is simply not shaped that way. 12 around 1, creating 60-degree angles, both radially and axially, with alternating tetrahedra and octahedra, is the closest packing. Fuller observations. Having settled on the most symmetrical and dense sphere packing to faithfully present the characteristics of space, we are ready to explore the shape and periodicities observed by Fuller. The reliable precision of these patterns indicates that they are molded by space, not by imposed design. What are these patterns that captured?
So sorry, hang on.
That's right.
There we go. There we go.
Captured Fuller's attention so long ago and kept it for 50 years. We start very simply with the phenomenon of triangular numbers, a sequence of numbers in which each successive term is equal to the previous term plus the number of terms so far.
Are you, John, are you catching that there?
Yep. Right. So these numbers can be generated by triangular collections of balls arranged as in a rack of billiard balls. The total number of balls in each triangle in a series of progressively larger groups is a triangular number. Figure 8.8 shows the first 5 groups. The first member of the sequence is 1. The second is obtained by adding 2 to the first to get 3. The third by adding 3 to the other 2 to get 6, and so on. Each successive number is generated by the addition of a row with one more ball than the last. The sequence of numbers thus generated, 1, 3, 6, 10, 15, 21, 28, is specified by n squared minus n for n equals 2, 3, 4. N equals 1 corresponds to 0, which is not strictly speaking modeled by a triangle. Right,
Okay, this is enlightening for me. If you don't mind, we can pause here and kind of take a look at this, because this n squared minus n over 2 is the famous relationship formula. And all of a sudden, I'm seeing it differently than I've ever seen it before. I'm not sure I understand what I'm seeing, but I'm seeing something different than I've ever seen before, I can tell you that. Richard, do you have any comments on it?
Well, I guess I could say ditto.
4 or 5. I get that here is we're stacking balls in hexagonal formation. If we stack 1 and we set up a second row, then a third row, then a fourth row, then a fifth row, we're seeing this kind of configuration. And somehow this relates to n squared minus n over 2. So that's interesting.
Well, for example, if you do number 1,
You're right.
N squared is 1 times 1 minus 1 is
0.
Is 0 over 2 is 0. 2 is 4 minus 2 over 2
is
4.
1. Right. 2 squared minus 2 is 4 minus 2, which leaves 2 divided by 2 is 1, right?
Mm-hmm.
Yeah, and so as he said, the first row doesn't count, like number 1 doesn't count. So he's getting n squared minus n over 2 gives you 1.
Right.
N squared 9 minus 3 is 6 over 2 gives you 3.
Right.
And
4 squared.
Oh yeah, 4 squared is 16 minus 4 is 12 over 2 is 6.
Now I got the 3.
So, there we are there.
But I don't get the 6. And then take it next step further. 5 squared is 25 minus 5 is 20 divided by 2 is 10. Somehow that's a 10. So
No, there's not something wrong here.
I wonder. The total number of balls in each triangle in a series of progressively larger groups is a triangular figure. We got that, figure 8.8, there it is. Shows the first 5 groups. the first member of the sequence is 1. The second is obtained by adding 2 to the first to get 3. Okay, so
Yeah.
there, he's talking about a total of 3 balls, right?
Right.
The third by adding 3 to the other 2 to get 6. Okay, I got that. I'm getting that arithmetic relationship between the first figure, the second figure, and the third figure. I'm getting that. Is everybody else getting that?
Mm.
The third by adding 3 to the other 2 to get 6. I don't understand that. I got it all the way up to number 3.
3 squared.
I think the
Nine
fourth one
minus
is you.
3 is 6 over 2 is 3.
They said an addition of a row of one more ball. So
Each
add one more
successive
ball,
number.
and it gets 10. I think the 1, 3, 6, 10, 15, 21 we can get. The problem is the formula, right? Because when you add the 4 balls at the bottom there, it makes 10 when you add it to the 6, right? And then at 5, you add 5 balls, which is an additional ball to the previous row, then you get 15. So those
15.
numbers make sense. That just now the formula is
Yeah.
not adding up the way we are seeing it. Yeah.
The sequence of
Well,
numbers thus
what it's
generated.
doing is giving you the total behind. So, for example, if you take 5 squared minus n, it's 25 minus, no,
5.
yeah, minus 5 is 20 over 2 is 10. And so that's giving you the numbers at 4, because that's 10 under the 4.
That's right.
And it works the other way too. If you do 4, you'll get 6.
Yeah.
Okay.
And so if you do 6 squared is 36 minus 6 is 30 over 2 is 15. So there should be 15 balls in that number 5.
Mm.
And there's 10 plus 5 is 15.
Yeah.
Yeah.
I think that, let's see if the next paragraph is making any sense. This might appear to be more difficult.
Okay.
Okay.
Johnny, you want to?
The triangular numbers. The formula n squared minus n might appear to be a more difficult way to obtain these values, and certainly for small groups, it's easier just to count.
Hang on, we'll get there. Count the balls. Right?
Right. But of course, for the 20th or even the 9th triangular number, it's far more direct to subtract 10 from 100 from 10 squared and divide the number by 2 to get 45 than to draw rows and rows, 9 rows of circles. Mathematics purposes a shortcut, otherwise known as a generalized principle. So far, we have a numerical progression, n squared minus n.
Over 2. That means
Over
over 2
2.
there, John. Yeah, go
That's
ahead.
right, it is. Yeah, it is over 2.
Yeah.
That happens to be modeled by triangular clusters. We might have chosen to discuss a variety of other sequences. For example, the numbers generated by n squared, 1, 4, 9, 16, 25, which could be labeled square numbers because they are geometrically represented by square clusters. But we have a specific motivation for paying attention to triangular numbers because of one especially significant characteristic. The nth term is the number of relationships between n items for n equals 1, 2, 3, 4. For example, suppose that for any given number of people, we wish to know how many telephone lines are required to link everyone to everyone else by a private line. The answer is the triangular number corresponding to a number of rows of ones less than the square of 2. 2 people require only 1 line. 3 people require 3. 4 require 6. And none produce.
See, this is now the formula that we're used to.
Right,
And that formula then gives you the number of lines between
right.
or the number of relationships.
Interrelationships, yes.
And so that's what kind of threw me off, because you see the other version of that equation, if you stretch it out, n squared minus n is actually n multiplied by in brackets n minus 1. So for example, if you said if the number is, say, 3, use 3 and use an n squared minus n, but if you actually change that formula so it's n then multiplied by, in brackets, n minus 1, then you get 3 times 2 equals 6. And divided by 2 is 3.
Okay, I just think
It's an
for
easier way to
me,
use it now.
yeah, I think for me, if we don't actually do this, I'm going, because this is like the second time this has come up, and if I don't actually run through this math, and I wonder if I should just use a spreadsheet because then we can kind of see this. Anne has gone to get some food, and it's taking a long time to load up because of whatever. Okay, so I'm gonna make a couple things here. So we got this formula n to the power squared. So n squared minus n. He uses the
Yeah.
low.
Start out with the other one.
Well, I want to show the relationships because I want to make sure I understand them too. So, but we can start with the other one if you want.
Well, what I was meaning by starting with the other one is start with n times n minus 1.
Yeah, that's what I'm glad to do. N minus 1. I do get that that's the same formula.
Right. Over 2.
Yeah, they're both over 2. We talk about whether or not they're over 2 based on whether we want to include the convex and the concave or not.
Right.
And what we're just doing is we're only assuming, if we, okay, good. So n squared. So if we pick the number 2 times 2 is n squared. Oh, geez. 2 times 2. I have to put the equal sign up there. That's 4 minus n minus the 2 equals 2. And then divided by 2 equals this divided by 2. Bam. Equals 1. So that is that formula right there. And what we can do here is we can set the value of n. Pardon me for being so pedantic, but here we go. And we use the number 2 here. And so what I'm going to do is I'm going to go up here and say, instead of 2, I'm going to go this guy. Whoops. That guy times that guy. D4. Okay. So now here's our manifestation of our formula. So now we can change this and go 3. And that means 3 squared is 9. Oh, that has to be minus, instead of minus 2, that has to be minus n. So squared, this should be 6. So again, this has to be this, this plus that. Okay, good, is 6. And then this has to be this divided by 2. Okay, So now I can take and substitute any number in here. And so I'm going to just move this over. We'll make that bold. And now we'll make that 4. So 4 is 16 minus 4 is 12 divided by 2 is 6. So now this number, we can plug any number in there and it'll do that. So now
Right.
let's come over here and do the same with this, okay? So this value is going to be n. And so now what we're going to do is we're going to go, we'll put 2 in there to begin with, and I'll make it bold. And I can even make it bigger so it's not quite so hard to read. Okay, good. Now, so n, so now we're going to go that times that minus 1. And it's not going to get, it's going to give me that y.
Because you didn't have the, oh, should have,
There we go. Right?
right.
Because that formula is, there we go. So that's right. And that would be, it would be 2 minus 1 is 1 times 2 would be 2. So that's correct. And then we're going to take that whole thing, and from here on out, it's the same formula. Is it? This formula is,
Well, you, yep, the first one you didn't divide by 2.
what?
What's there?
That's divided by 2.
Yeah, but on the
You got it
second
in the
column,
formula, but did you do it?
the second column where you started out with 2.
Okay. Oh, well, I'm dividing by 2 right here. Let me see. I'm going, let's do 5 so that we can see our same numbers. Minus 5 is 15. That is divided by 2.
No, but there should be there's no minus on this one. It's just simply, it's
Okay,
5 times 4 is 20 over 2 is 10.
well, what this says is it says F4, which is 5,
Yeah,
times F4 minus 1.
right.
That number is 20.
And
So,
divided by 2
okay,
should be
20.
10.
Oh, I see. If we cut off all this crap and just divide it by 2, equals this divided by 2. All right, so now the formulas are the same. So if we set this value at that value, and then we can come over here and say this n value is 10, we get the same equals over here.
Right.
Okay, good. So 8.
And now that, in what we have been using, that is the number of interconnections between the numbers. So
Right.
if
And
you've
I'm,
got 8 nodes, and you'll have those 28 interconnections one way. If you took the 2 off and didn't divide by 2, then you got two-way interactions.
wait, hang on a second, because I want you to
Until
say that
you
again.
got them doubled. So it's like if there's 4 of us, is there? Yeah, 1, 2, 3, 4 of us. So 4 of us right now there's 6 interconnections between the 4 of us. But if we were doubling that in the sense I'm communicating to you and you're communicating to me, that's 2. So overall, there's 12 interconnections that are going on. So if you ever wonder what's the complexity, why are communications complex, that sort of tells you.
Yeah. So let me see here. I want to get this guy. I'm trying to copy this. I'm going to put him in here. He doesn't want to paste. So let me just drop him in. He doesn't even want to drop. I know I've inserted pictures before. This bothers me. You know what? I started writing my book a couple years ago, and I've stopped working with spreadsheets, and it's driven me crazy. Okay, so now thank you, John and Ann, for being patient with me while I work on these two formulas. Because these two formulas are the same formulas. Now, this guy here is not in Amy's book. This is the guy that's in Amy's book. And, but Richard has had experience, and we've in the past, I don't know where we learned this formula, but we learned it from someplace.
Well, I learned it because I thought there were two different formulas, and I was having trouble with it. And so, on one of our PrimTab meetings, I raised the question, and Kirby Uner, who is really big into mathematics, he answered it right away. He says it's the same, because he said you spell out n times n minus 1, and you get n squared minus n.
Right.
And it was like, oh my God, there it was right in front of me.
Yeah. And this is an easier formula to cope with, I think, with most people's math than working with squares.
Yeah, because now all you do is get the number.
Yeah, it's just
any number, and minus 1, multiply it by minus 1, so it's 4 times 3, 5 times 4, 20 times 19. It's so easy.
It's so easy, but I'm not sure how it relates to what we're reading here.
Well, that's just, what it's throwing us off is that she's saying in here that same formula gets you the number of n's, and not the number of r's, or the number of relationships, which is I'm comfortable with. But then when we were looking at the diagram and the n formula that she's talking about is giving you the number behind.
Yeah, it's the number behind.
So I can't quite follow that. I don't know whether if we read the text again, whether we would see that that's what she's saying. But
well, that's what we seem to notice when you did your calculations. That's what I was noticing here. Whoops. Is that we do n squared, so we'll start with 3. N squared is 9, minus 3 is 6, divided by 2 is 3.
yeah, so that's the answer to
the item number 2.
Item number 2.
Yeah, that gives us the previous formula. So if we take 5 squared is 25, minus 5 is 20, divided by 2 is 10, and that's the answer we get for this.
Yeah,
And
so there's something up in her description that has to do with 0.
Yeah, the first number of the sequence is 1. The second is obtained by adding the 2 to the first to get 3. The third by adding 3 to the other to get 6, and so on. Okay, that's how the stacking occurs. Each successive number is generated by the addition of a row with one more ball than the last. Okay, we got that, right? That's what's happening here. Each row added below has one more ball than the last. So we got that. Now then, she says, the sequence of numbers thus generated 1, 3, 6, 10, 15, 21, 28, etc. And she only goes to 15 down here.
Mm-hmm.
So the sequence of numbers to 15 is specified by n squared minus n over 2 for n equals 2, 3, 4. In other words, n equals 1 corresponds to 0, which is not strictly speaking modeled by a triangle. That's the part I don't get.
Can I try this?
Yes, please.
This is just maybe if you keep it just maybe we are supposed to keep it simpler in the sense that maybe they're trying to point out to us that the coincidence of the two sequences are uncannily exactly the same. So maybe that's it. And maybe she's going to lead us somewhere with it. I'm just saying.
Maybe she will. But
Yeah.
in spite of these words I'm reading, what Richard said seems to be true. If we calculate the n squared formula on 5, we get the number of balls in 4.
Yeah.
So, and I don't understand why she hasn't explained that so far. She says here the formula n squared minus n over 2 might appear to be a more difficult way to obtain these values,
Mm.
and it certainly is for small groups. But when we get into larger numbers, then the formula is much more handy. I agree.
Okay, let me share this, the discovery I made about math, trying to teach it to children, right?
Okay.
Because we in Asia, there's this tendency to always go for formula, and kids having to understand formula.
Mm.
Melinda, my sister, myself, when we went down this path, it's all about discovering the formula.
Mm.
So one of the things that came up was we were attempting to deal with fractions, for fractions, and because you know how teachers teach it the shortcut way, right, with a formula or with a method. Like if you do half divided by half, then you're supposed to make it a multiplication. The next line is half, and you multiply, and then you flip the other half over, and it'll be 2 over 1, and then you start crossing it out, and then you get answer is 1, right? So for the longest time, even when I was a kid, why is multiplying and multiplying, you get a smaller number, but when you divide, you get a bigger number. So until this is under the Montessori system. It's so they created this guy, Jerry Mortensen. He created this math called Mortensen math, and the way he explained math, it's actually the language of math, right? So when you go down the path of the language of math, then the formula starts to make sense. Okay, so you have to understand the language of divide, because all symbols you have to link it to the language that goes with it. So when you do division, it's how many. Let's say if you do 3 divided by 3, is how many 3s can you find in 3? So answer is
1.
1, correct. So how many 3s can you find in 6? So when you say 6 divided by 3 is how many 3s can you find in 6? So the answer is 2, because you can go 2 groups of 6s. So when we went down the path of this division, he came with this understanding of the language of division. Then the fractions start to make sense. Like how many halves can you find in half?
There's
Answer
one
is
half and half.
1, correct? So it's 1. So, but you can show it when the numbers are really simple like this. But what happens when you have 3/4 divided by 5 over 7? So if you go down the language part, it doesn't, you can't answer it, right? But because they found this pattern of a way to divide, and then the method is if you flip the number around and then you multiply the top numbers and the bottom number together, so the top numbers will give you the top and the bottom number will give you the top after you simplify the numbers, right? That you can use to calculate any fractions. But the thing is, when you teach it directly into formula, it doesn't make sense to anybody whose brains are not wired to see the method. Does that make sense? But as it gets more complicated, the numbers, the formula works because it's a pattern that they discovered. So what I see now here is the same thing, exactly what Amy said, right? Because when it's small, you can add it yourself. But the minute the numbers get bigger, how to know the number of balls prior, like the row and the rows before, you can use it to calculate. Yeah, you use this formula to calculate. Yeah, and I think it's just right now it's to point out that both calculations seem to produce the same sequence. For the moment, that's what I get. Does that make sense?
Kind of. I mean, I've actually worked, Manu, we're on page 123. Let me see, 124, 125. We're right at the bottom of 124, going to page 125 in Amy's book. And we're taking a look at the triangular numbers here. So that's what our conversation is on these fuller observations. I get the math. I think I get what you said about fractions, but I'm lost in that for some reason, the n squared or the n squared minus n over 2 formula gives me the previous stack of balls. That I'm not, I mean, I see that it does, but that
I
does
think the
not
main
make
thing-
any sense. What?
The main thing why we are comparing the two is more, I think, because it just produced the same sequence of numbers, the same sequence. It's exactly the same, you know.
Right.
But yeah, but what is calculating? Both are calculating different things. That's what I'm getting out of what she's saying by when the numbers get bigger, then the formula works, you know, and you don't start drawing circles. You just use the formula and you'll get the number. But yeah, maybe Manu can help us there as well.
Well, and I just got a little epiphany. The formula n squared minus n over 2, or the formula that Richard's talked about, which is n times n minus 1 over 2. So, and we did that math on that, Manu, and here's the math. So here's the n squared minus n over 2, and here's the n times n minus 1 over 2 formula right here. And they both get the same, they both have the same outcome. But what we noticed is when we took this number 5 and we did the n squared formula over number 5, it gave us the number of balls in 4. But here was my epiphany. That formula gives us the interrelationships between with the number 5. In other words, I tried to get this and I didn't get it, but whoops, there's that. When we see this guy right here, that formula gives us the number of lines between the spheres. And I think it's coincidental that it's giving us the balls, but it must be significant in some way. In fact, let's see what my computer's doing. Okay, good. My computer's bringing up that picture right there. And so the formula gives us the number of lines between the number of spheres or nodes. And so we've got 4 nodes, but we've got 6 lines. Now, I have another chart of it over here that I think is really cool. Is this yeah, this is a PNG file too. This is really good because this shows the same formula, but it shows it in a graph. So I think all I'm doing here is establishing the problem for me. I hope it's not too distracting. We'll just start reading when you're ready to read. But here's a chart that I did to explain the relationship. Because I asked myself, why is it that when Bucky is taking a look at a tetrahedron that has 4 nodes, A, B, C, D, why when he described it did he call it A, B, B, C, C, D? Why did he use those numbers? Why didn't he use B, A, C, B, D, C? And here's what he did. He went A, B, B, C, C, D, and then he went A, C, B, D, and then to A, D. And he left off this side. So I've concluded this is the convex and this is the concave. This is the divided by 2. So we get our number over here. And if we want to know the total number of concave and convex relationships, we don't divide by 2. Richard and I kind of discussed that earlier. Here's the concave relationships, here are the convex relationships. Instead of being in a chart like this, I put in a chart like this. And this gives us a total of 720 degrees in the tetrahedron, by the way.
Yeah,
So,
and if you also use, instead of saying concave and convex, you say two-way or interconnected, then you get the communication going both ways.
right.
And so you don't divide by 2.
Right. And to be clear, in a concave relationship or in a one-sided relationship, A relates to B, and B relates to C, and C relates to D, but B is also relating to A, and C is also relating to B. That's where Richard comes in with this two-way relationship. And too many times we look and just say, well, A is relating to B. Well, but the degree to which A will relate to B depends on the degree to which B will relate to A.
Right.
It's a two-way street. And we don't tend to think in terms of two-way streets. So what dawns on me is this formula is not about the number of balls. Coincidentally, the formula on n squared minus n over 2 gives us the number of balls, but what it's counting is the interrelationships on a graph that has 5 nodes. And I have another epiphany that I'm just going to throw out on this. This is a hypergraph. This is a formula for a hypergraph. Anytime you put a number of dots on a sheet of paper, or say these are the realities with which we are dealing, this formula, n squared minus n over 2, is going to give us the number of interrelationships that are there. So if I put 17 dots on a page and I want to connect all those dots to all those dots, that's exactly the formula I'm going to use.
Right.
This is a formula for a hypergraph. A tetrahedron is a hypergraph. In a sense.
Hello.
Yeah.
Good morning.
Good morning. So you jumped in when we
Hello.
were kind of in the middle of a thing here, and we can kind of pause here for a minute. How you
I
feeling,
can
Manu?
see John is there. Cool.
Yes,
Yeah,
I'm
John
here,
is here.
Manu.
How are you?
Well, thanks.
Okay. Can I explain this? It's quite simple.
We'll see. We'll see how simple it is, Manu.
Okay.
ahead.
So you talk about hypergraph. That's one of way of teaching mathematics. Let me just do this. Let's say you have a set of n elements, and you want to check the interrelationship that are possible. Do you see my sheet of paper?
Yeah, if you hold it a little bit closer, we'll see it a little bit better. And everybody, do you know how to pin Manu to the main screen? If you put your mouse over Manu's picture in the upper right-hand corner, there are 3 dots. When you click on those dots, you'll see the 4th or the 5th menu item down says pin. If you click on him, he will then become full screen. So everything he shows.
Okay. So let me take the first element.
I'm going to.
Yes, I'm going to come to you. Just quick. I'm doing this.
Well, let me just, while you're doing that, let me just share with everybody what it will look like if you've hit the pin button. That's what it'll look like. Everybody will be stacked across the top, and Manu will be really big in the middle. And you do that by catching those 3 pins in the upper right-hand corner of Manu's deal. Okay, Manu. So, you guys didn't see that.
I'm here.
Yeah, but hang on. Let me show everybody what I just described. I thought I was showing everybody. So here's what the screen will look like, you guys, if you pin him. And you pin him by taking a small picture in the upper right-hand corner and say pin. And that's what you'll get. Okay, good, Manu. You got the show.
Am I coming? Okay, good. I'm coming now.
We've got you
Hold down.
pinned, my man.
I'm coming. Hold on.
Sam and Dave. That's Sam and Dave. You
Hold
can't
on.
beat Sam and Dave unless you're Otis Redding.
Okay. You see this?
Yeah, if you hold it right. Okay, we see that. Do you guys all see that?
Okay.
Mhm.
How many colors? There are 4 elements, right? In the set.
Yep.
Hold it a little bit higher. Okay, there are 4 elements on each side. You got 8 elements.
Yes. And each has
4 relationships.
There are 4 4 relationships, right?
Sorry, so each has 3 other relationships.
Yes. But each are painted different, different colors.
Yeah.
Green, yellow, red, and orange.
So each has 4
So you've got 12, have
relationships.
you?
Okay.
12
No,
relationships.
each has 3 coming out of each X.
No, 4. 4
4
No.
because
coming out.
here, hold it up a little bit. Hold it up a little bit more, Manu, and I'm going to take a picture of it. Hold it up again.
Okay, this is a set, right? And imagine that there's a mirror here. So this set duplicates the other way. So the same set is there.
Okay.
Okay. So can you see me? I don't see the screen anymore. Okay. Right.
Good. So there's your little deal. And there's 4 nodes over here. And there are
Yes.
4 nodes over here. And every node has 4 lines off of it because every node connects to all of the other nodes.
Okay. So imagine initially it was the same set. It's a set of four elements. And then you put that set in front of a mirror. You have the image of it the other side. You see 2.
Okay.
And imagine that each of the initial is relating to whatever is across in the mirror. So there, as you see, you have 16 relationships, right?
4 times 4 is 16.
Yes. 16 is the square of 4.
Well, the
Okay.
formula says it should be n squared
No,
minus
wait,
n.
wait, I'm coming. 15 is square. I just want to make sure that the
Okay.
first concept.
Tell me how many
16.
interconnections there are.
16, because you have 4 yellow, 4 red, 4 green, and 4 oranges. Okay. Now, it is the same set. So you cannot say I'm in relationship with myself.
That's right.
It doesn't count. So you have to retrench from that n square the number of elements of a set minus n.
Yeah.
That is
There's 12
the second.
relationships.
Yes, because I'm in relationship with myself. Yes, I'm in relationship with myself, and that's it. It doesn't go anywhere. It doesn't communicate anything.
Well,
And
it
the
does
third thing,
communicate something at a metaphysical level, but go ahead.
okay, at the physical level, see, okay. The third thing is that it is symmetrical. If I'm in relationship with you, you are in relationship with me. You can verify it there.
Well, the thing that's missing, Manu,
No,
see,
hold on. I haven't finished, Richard.
Okay.
So if I'm in relationship with you, you are in relationship with me. It means that in the what we are counted twice. So the number of independent relationship is n squared minus the n that represents the relationship
yeah,
of me to me,
right,
divide by 2,
right,
because you counted twice.
right.
Okay. So
But your
that is
your model doesn't show that.
it shows that exactly.
Okay, do the formula and get the answer.
Okay, take the element. Put in
There's
the
8.
first one A, B, C, D.
No, how much? Just count them. There's 8.
Are there 8, Manu, or are there 4 in a mirror?
No, they are okay. A, B, C, D, A, B, C, D across. Right?
So
If you do the
A1,
if A is in relation with B, the same B is in relationship with A. Say in this example, for example, if I take A in relationship with B in red, B will be in relationship with A in yellow, in orange.
Yeah, right.
So it's counted twice. When I say there are 16 that are counted, it's counted twice. Everything is counted twice.
Take your x's, and are they 4 plus 4? Are they 8 nodes?
No, I don't need nodes. I have say you
Are
say
they
that
8? Are they
you have
8
a set.
x's then?
Richard, you say you have a set of a number of people. I don't even know what number. I just took 4 as an illustration. And I want to demonstrate the general formula of n squared minus n divided by 2.
Yeah.
Or sometimes it's also put in n times n minus 1 divided by 2 is the same thing.
it's the
That's
same
right.
thing. That's what we showed earlier.
Yes. So if you do that, the minus n is because I'm in a relationship with myself.
Yeah, we
It
know
doesn't
that,
count.
Manu, we know that.
And the divided by 2, I can only be in relationship to a set, to a number of relationship that can come out of me
that's right.
is the number total of set of element minus 1.
That's right.
Okay. So n times n minus 1, and because I count twice, if I'm in relationship with another with Richard in relationship with me.
That's right.
It's called symmetry. So then I have to divide by 2.
No, you don't divide by 2.
I do.
The formula
it's-
does.
If there's
If-
two-way relationship, then you don't have to
The
divide.
formula
Yeah.
divide by 2. I have a formula here. The formula is at the base, page 124. Read it.
Yeah, I got
We're,
it.
we're
Yeah.
reading it, Manu.
Yes. What? You don't divide by 2?
Well, here,
If you have a two-way relationship, you don't have to divide by 2.
right, here we
No,
go. Let me show you what Richard's talking about. Okay, we talk about the a squared plus b, or we talk about the tetrahedron, A, B, C, D. And we have 4 nodes there, and they all interrelate with each other. This is a hypergraph on 4 nodes. I wanted to know why when Bucky explained this, he called it the relationship ABBCCD, ACBD, AD. And when I did a graph on it, here's the graph I came up with. I put ABCD up here. I put ABC down here. And of course, I went A to A and B to B and C to C and D to D. And you said they don't count. And I'm going to say they don't count physically, maybe, but they count metaphysically because they're
No,
actually
they
there.
don't count. They don't count in the
Okay,
tetrahedron.
hey, whoa. Don't tell me they don't count. They're on the graph.
They don't count on the tetrahedron. That's what I'm saying. They don't. And this is it. I defy you on that one.
But Manu,
Yes.
I'm
Yes.
trying to explain something. I'm
You are
explaining
explaining. Okay. Let me show
I'm
you.
explaining why Bucky picked the elements he picked. And as you stated, he left off the A, B, B, C, C, D, D, the A squared, B squared, C squared, D squared. And in doing so, came up with the convex and concave. But I'm pointing out those things still do exist in space, and they have a metaphysical significance. This side here is concave. This side here is convex.
No, it's a vertex, Steve.
It's
That's
the
all.
other way around. This side is
It
concave.
is AA, BB, CC, DD is a vertex of vertexes
Yeah,
of a
but
tetrahedron.
that's
what
not
it
what I
is.
was saying. That's not what I was saying. I was saying something else. I was talking about concave and convex. Do you have an opinion on concave and convex?
There's no concave and convex on this relationship here.
Well, and I'm pointing out that most likely one side of this or the other is concave, and whichever side is concave leaves the other side as convex.
No.
This graph right here does not show the AABBCC. I just drew a line down in between it like that because I acknowledge that in physical space, these seem to be, they don't
Steve,
count. Yes.
do you realize that representation is a representation of relationships?
Of course I do. That's why I drew these charts.
Okay. So AA means that A in relationship with itself, AA in the physical representation that you have of a tetrahedron is the vertex A, vertex
Good.
B, vertex
Right.
C, vertex D. It's an
Right.
element. It's what I call the element. The 4 elements of a set.
Yeah.
The other stuff in there are relationship. And every edge of a tetrahedron is a double relation. Is vertex A in relationship to vertex B and vertex B in relationship to vertex A. That's all it is. It's a double relationship. But when you're counting about the independent relationship between elements, where the generalized formula comes in, that's the way.
We understand that.
So
We
what else
understand
is there? Yes.
Well, what else is there is the other questions we were asking when you came in. Does everybody see these? Everybody see these charts?
Mm-hmm.
Yeah.
Okay, so
Yes.
I found them to be very helpful. I spent probably 40 or 60 hours going through this. to develop this relationship, trying to explain Bucky's relationship. When he describes them, he says A, B, B, C, C, D, A, C, B, D. He says these. He only talks about these sides. He talks about this row first, this row second, this row third. And this is in the cosmography thing. Anyway.
Because it talk about it like that because it is symmetrical. Because
That's
of
right.
the principle of symmetry.
Right.
Okay.
So
when I'm talking about the edge, let's just say you have a tetrahedron A, B, C, D. A, B, C, D.
you got it right here.
Okay. No, I want to put it here. When you talk about this tetrahedron, if you take this edge, A to D, whether I call it AD or DA is the same thing.
You call it what?
Whether I call this edge,
That's right. That's
painted
why
in green.
there's 6. That's why there's 6. N squared
Yes.
minus n over 2 is 6.
Yes. No, n squared minus n divided by 2 is 6, as you say.
That's what he said.
Yes. It's because when if I say AB, AD here, or DA
Yes,
is the same thing.
Manu, we understand that, but
We understand that, Manu.
it's independent. If it was two-way, then you didn't have to divide by 2. It would be 12. That's all.
What is it?
If the relationship, the edge, was 2 ways, then you wouldn't divide by 2. You would have 12 interrelationships.
Are you saying that this formula is wrong?
No.
No, you're not hearing the conversation. So
Yeah.
he's definitely not saying it's wrong. Let me
Yeah, if you
point
don't
out.
say it's wrong, why don't we progress? Why are we discussing this?
Manu, you came in
Okay.
late to the conversation. We had
No,
3
I
or 4
understand
questions.
you. I listened to you for a moment.
I
Why
know, but
don't we
read pages 30, read pages 124 and 125, and then listen to our question. You'll understand. Here's my point, you guys. When Bucky,
So
this
what's
is
your question on this, Steve? I want to understand you. What is your
Well,
question here?
Let me
on
get
this
back to
table?
that because I'm afraid people don't understand this particular element. When Bucky explains his A, B, C, D relationship, he explains it this way: A, B, B, C, C, D, A, C, B, D, A, D. I looked at that and said, now, why did he do that? Because he took A, B, C, D, and he went A, B, B, C, C, D. Let me move this over here. Let's see if I can move it over there. Because I wanted to think like Bucky. So when he did this, he goes A, B, B, C, C, D. There it is, A, B, B, C, C, D. Then he went A, C, B, D. There's A, C, B, D, and then A, D. I built this chart trying to think like Bucky. And when I built this chart, I said, oh, well, he did all these, but he doesn't describe these relationships. And look, he's not even acknowledging the square of the nodes. So when I looked at this, I wanted to know why he named it that instead of something else. And so this was my attempt to think like Bucky. Now, in that, when we start doing this stacking thing in the book, which we're doing now, he brings up a couple points. And we can read this again so that you can understand what our question is, if you'd like, Manu.
No, just continue, please. I think that I will be wasting your time.
Well, it would be wonderful if you understood what the problem was from our point of view here. Go ahead, Anne.
Yeah, can I try this? Okay, because okay, I can see that that the two, we're talking about two different things here, right? One is exactly, I think, was it Richard or Steve that you said metaphysical? Okay.
I said metaphysical, yeah.
Yes, you're coming from the metaphysical space. So I'm going to come from the physical space first before I share something that happened yesterday at the TEDx for children, and what this 15-year-old said, right? That will take care of the metaphysical side. The physical side, I think they're just looking at it very simply based on the physical math or physical science of it, I suppose, on the actual numbers, right? Because when you do AB or BA, actually the answer is the same. Because mathematically, if you multiply AB, you can write it as AB or BA. Does that make sense?
Sure.
So in math, it's like one entity. Okay, so if
But,
you
and it's only that if it is symmetrical.
no,
The
no, no.
relationship that are
Manu,
not symmetrical. Yes.
yeah, Manu, I'm not talking about the metaphysical side. Yeah, just talking about even because even mathematically, because when you multiply, it's either or. You can write it either way, and the answer is correct. But it's one, right? But the metaphysical side, and the formula does not take into consideration the metaphysical side, and your diagram, Steve, is taking
Yes.
care of the metaphysical side, because
Absolutely true.
yesterday a 15-year-old boy, spoke about this. The title is "I'm Alone, but I'm Not Lonely." He is Gen Z or Gen Alpha now, Gen Z, yeah, he put down. So he talked about being very hyper connected, right, in their generation right now. However, he does take time out to spend with himself. So he talked about he has a relationship with himself, and and so when he's alone, he doesn't feel lonely, because he does talk to himself, whether it's in his head or he talks loudly. But he says when he goes through some stuff, why don't he can even ask his 8-year-old self, and he can project it forward, and he can talk to his older self, just to look at things from different perspectives. So I thought it was a beautiful talk, and that in itself demonstrates the metaphysical side of relationships, right? Because we can have a relationship with ourselves, especially when we're talking in our head. And then the other thing is that when you talk about two-way relationships, yes, it is two ways, because for some, the relationship may not be different, may not be the same. A dealing with B and B dealing with A, sometimes it's not equal. Sometimes A is of a higher position, or at home, more in a more respected position, etc. So and one may communicate more, the other may communicate less. So there is a two-way thing. So we are coming to the metaphysical side. So I think we were trying to make sense of this relationship thing. And so when you look at the formula, it's just one-dimensional, which I wouldn't use one-dimensional. It is based on physical, counting, rather than the actual metaphysical side of a relationship. So I'm just pointing out what I understand from the whole discussion this morning. Okay.
No, and Ann, you understand it
me,
exactly the way I understand it. Joe had his hand up. Let's see what Joe has to say, if we may. Go ahead, Joe. Yo, Joe, you're
Sorry
muted.
about that. Sorry about that. I'm kind of was trying to unmute there for a moment. But no, I think what Ann is actually saying is really important, because I was actually even talking about somebody about using a visual way of communicating and using symbols. And one of the things that really always comes up is how do you depict the relationship when there's a power dynamic? And so that you start to, and they have a very interesting way of depicting that, so that you have an understanding of why somebody may be saying something a certain way. That's one aspect of it. But I think that there's another important point that Ann made, that there's a distinction between, the nuances between A and B. There's a distinction between loneliness and solitude, and that is an important distinction to be able to make when you're evaluating the relationships between A and B, and B and A. So it's not necessarily just you're not looking at it in a binary way. There's a more a deeper way to actually evaluate the relationship. Anyway, that's just some thoughts really quickly.
And the
Okay.
deeper way is what we described as a metaphysical way, as opposed to the physical way. Joe,
Correct.
that's what we were saying before. Okay, good. So go ahead, Richard, your hand's up.
Yeah. What's exciting about what Anne just did, for me anyway, is that when you add in the relationship with yourself, so you use the formula n squared minus n over 2, you get 6 between those four. And since we acknowledge you can have a relationship with yourself, then you add 1. So it becomes 6 plus 1 equals 7. And that accounts for that relationship you can have with yourself and the 6 other interconnections with others. And if it was two-way, then you wouldn't have to divide by 2, and you would end up having a total of 12 plus 1 is 13. It's beautiful because it includes the notion of interconnecting with yourself along with interconnecting with the others.
True.
So it's and again the thing that and Manu can maybe really help us with this, because what got us stuck, Manu, when we read Amy on that page, she said that you can determine the number of balls with the same formula. And we've been used to using that formula to determine the number of relationships. So it started to get confusing in terms of how can the formula be used to get the number of balls as well as the number of relationships.
And what we determined from what Richard just said is we take the formula on 5, we do 5 squared minus 5. 5 squared is 25, minus 5 is 20 divided by 2. That's exactly the number of balls in the previous set. That's what Richard just said.
First, this formula has been demonstrated. It's a general formula. It's not something she's inventing.
We know that she didn't invent it.
Okay. So it's been demonstrated. It means that it is true everywhere.
Well, Bucky invented it in his cosmography book.
No, it didn't.
Before that? It was before
Yeah,
that.
I learned this thing at school. What are you talking about?
Yeah.
I did it ad nauseum. Ad nauseum. I did it at school.
Good. Wonderful.
Well, the thing
in what we call algebra, we did this thing ad nauseum. What I'm saying is that the thing is very clear. Is that if you have any finite set, the number, that formula is to determine the number of relationship between distinct members of a set.
Manu, we got that. But
we got that, Manu.
No, hold on.
What this page, Amy's work is saying that same formula gives you the number of nodes
in the previous set of 3.
Yeah, in the previous set. And so we're questioning. We want to understand how that same formula can get you the number of relationships and the number of nodes or corners.
Because for God's sake, n is the number of nodes.
But it's
if I know n is the number of nodes.
Yeah, but what we're saying, what she has said here, is that it's the number. When we perform the formula on this number 5, it tells us the number of balls. Not only does it tell us the edges in a number of 5, it tells us the balls in the number of 4. Here's what it says. The formula n squared minus n over 2 might appear to be a more difficult way to obtain the values, and only certain for small groups, it is easier just to count the balls. But of course, for the 20th or even the 19th triangular number, it's far more direct to subtract 10 from 10 squared and divide by 2 to get 45 than to draw all the rows of balls and count the balls. So not only does it count interrelationships, Manu, it counts balls.
Okay.
In the previous set.
I seem to understand where you are getting confused.
Where we're getting confused, we're not confused, Manu.
No, let me say something, and then you get it. You can't talk of vertices without talking of a relationship. The two go together.
We know that.
Okay. That formula gives the relationship between the two.
It also counts the number of balls in the previous set.
No, it doesn't count in number, but I don't know what
It does. I'm reading it.
What?
We can read it.
Look
Oh,
on the
read it,
page.
Steve. Read it, because I feel that there's a lot of things that I said here that are not, that just don't make sense.
Well,
Well,
that's
read
because
it.
you're
That's
jumping
why
in the middle.
we're
Here it is.
Okay, read it. Let's listen. Let me listen. Read it.
You read it.
No, you read it.
Okay, the formula n squared minus n over 2 might appear to be a more difficult way to obtain these values, and certainly
Which
for
values?
the values of the number of balls. If I read it, it'll say that. And certainly for small groups, it's easier just to count the balls. But of course, by the time you hit the 20th or even the 19th triangular number, she's talking about triangular numbers here, Manu. This is our conversation. It's far more direct to subtract the 10 from 10 squared and divide by 2 to get 45 balls, rather than to draw the rows, 9 rows of balls or circles. So she's talking
But
about.
Steve, it's that simple. You can do that stuff. Switch. Look at my sheet again.
Well, I don't.
No.
We've
no,
looked at your
Yeah,
sheet,
look
my
at
friend.
look at my sheet.
I
please.
am looking at your sheet.
Okay, my sheet here appear, my sheet, as I say, appear very complicated and messy.
It's not complicated and not messy. We
It
understand it
is.
completely.
If the number of nodes, that is the number of elements, grows a little bigger, you can't do anything with. It's very difficult to count.
Yes.
A formula is a lot easier. That's all she's saying.
Mm.
She's
No,
not,
she
not
isn't.
inventing.
Well, I think she's saying more than that, Manu. And you have your
No,
hand up.
she said,
Yeah.
Steve,
Please
Steve.
don't tell me no, Manu.
No, I say no in this case. I say no because
You
I
say
know
no.
better.
Don't, but I prefer you don't tell me no.
Okay,
You
so
can tell me you have a
I'm
point of
saying
view. Yeah.
you've read, it's not the point of view. You read something. I say again that what she's saying is that to represent it graphically in hypergraph is a lot more complicated than having a simple formula from which you deduct and find whatever you're calculating.
But Manu, she's not
Yes.
counting the interrelationships in the hypergraph. She's counting the number of nodes in the previous set of 3. Please
Steve,
read.
do you
Get your book,
do you
Manu, and
if
read.
I give you
Read page
Steve, I've read,
124.
I've
It's
read it.
it counts the
You
number of
told me
balls,
I read
Manu.
it.
It counts
Okay,
the number of
Steve,
balls.
let them make me Charles, please. Let them make me a ball between you and me. I beg you, continue, and then take time and go and read.
Okay,
You know
good.
that what you are saying, yes, please.
I'm
I
happy
beg
to
you
do that.
just to say that.
Anne has her hand up. Go ahead,
Yes.
Anne.
Yes.
Okay, I think we're at cross purposes here, but we're talking about very similar things. Hold on. Because she never said that the two are interchangeable. She never said that the two formula can be used, formulae can be used. Like say, if you want to count the balls, you use the relationship one. And if you want to count the relationship, you can use the ball. She never said that at all. So I don't think she's saying that those two are interchangeable. She's saying that the two have got the same numerical sequence that's coming out. So the amazing thing is that these two are counting two different things, and the formula is there, and yet they are producing the same sequence. I think that's all she's saying. So the one about easier when the numbers get bigger to count, it is more to count the balls, nothing to do with the relationship part.
Exactly right.
Hold on. I beg to differ, and I differ deeply. I want it to be recorded. I differ deeply.
Okay, that's because you came in late, Manu.
No,
and you're not hearing the conversation, my friend.
No, listen to me. For
okay,
once,
we will.
Because you always interject when I speak. I'm saying this thing here, that, and the formula is the same thing. It's two representations of the same thing. You are counting the relationship between elements of a set. What is given to you from the beginning is the number of sets. Either you have a number of relationship, you find a set, or you have a set, you find a number of relationship. That is what you call an equation.
Okay, good.
That's what is given. And fundamentally, if somebody says it's different, I
Okay.
clearly that
I
is
think I get
fundamental.
where you're coming from.
I'm
Manu, I
not
think I
coming
get
from anywhere, and
Mm.
on this thing is orthodoxy that I'm
Mm.
expressing here. It is what it
yeah,
is.
I get it.
Okay.
So if you have 25 balls right there, there is exactly the number of relationship either way you count it.
Yes.
Yeah. So I think
If somebody gave me the number of relationship, let's just say 6 relationship, I know that is a tetrahedral. I will count 4.
Yeah.
Four vertices. If somebody
Mm.
gave me 4 vertices, I'll count 6 relationships.
Yeah. So now coming back to Amy as she's talking about that triangular thing, her counting is she's showing us that that actually she's just showing us that when you look at the last row, the number of balls will give you the total. When you use the formula, give you the total of the balls above it. Okay.
Yes.
And that's all. I think it's just that's it. Yeah. But it just so happened that it correlates with the relationships. I think that's what I understand of it. Yeah.
But
And I
there's
think
the whole purpose. That's the whole purpose of algebra. Algebra is made to make relationship between set simple.
yeah.
By deriving general formula that are built into things, to make you calculate it simply. Otherwise, why do we do algebra?
Okay, but
it does count the balls. It does count the balls too.
it
So
also
it's
counts the balls, Manu. It also counts the balls. And let me read to you. I've taken Amy's language and put English into it because she wrote it very obtusely.
But did I say she's not? Did I ever say she's not counting the balls?
But she is counting the balls.
No, I never said that she's not counting the balls.
I didn't. I'm just going to read you what Amy says, and I'm going to insert. In fact, I'm going to insert. Let me do this so that you could read along with what Amy wrote, and then see how I added some words to see.
I
what
have
you
it
think.
here on my book. I'm reading also. I have it here on this page.
Okay, please let me just conduct the meeting here. She says the formula n squared minus n over 2 might appear to be a more difficult way to obtain these values, meaning the number of balls in the previous set of balls. And certainly for small groups of balls, it's easier just to count the balls. But of course, for the 20th or even 9th triangular number, it's far more direct to subtract 10 from 10 squared and divide by 2 to get 45 balls than it is to draw rows and rows, 9 rows of circles or balls. So she's talking about balls here. She's not talking about interrelationships at all.
Steve, please, let us just go across this and continue. Because what you're saying that doesn't, what you say, your last sentence doesn't make any sense.
Well, I just am reading Amy. So
no, I say what you say, your comment that you make, please. You are reading things that are precise, where people have spent time putting on and demonstrating in their life achievement. Don't make those light comments.
Don't make what?
Light comments.
Don't make the last comment?
Light, easy.
Of a row.
Flippant comment.
I don't understand. Are you saying light, L-I-G-H-T?
That formula.
Yes, he's saying flippant.
Yes. Yeah. That formula is.
I'm not being flippant.
Yeah.
The formula the formula says very clearly that the number of interrelationship.
No, Manu, I'm conducting the call. I'm going to tell you you're missing the point. She is counting balls.
I'm not missing any point, Steve, and I shut up here.
Manu, she's counting balls.
Sorry. I'm going to mute myself.
Okay, she's counting balls, Manu. That's what, look, count balls. This whole thing is about counting balls. It's not about counting any relationships. So we're going to continue reading from this point.
Yeah.
One more ball than the last.
Okay, good. Richard, do you mean to be talking? Because
No,
you're,
I'm talking to myself.
okay, good.
I'm having that relationship that Anne was talking about.
Is that one relationship or two, Richard?
Well, sometimes, yeah, my mind talks back to me, so that's two.
And yeah, we tell it to shut up sometimes.
You can turn off. Okay, good. Let's continue from here if we dare. I get that it's counting balls, so I'm grateful for that. Thank you for your patience with me. Okay, John, do you want to continue reading from so
Yes,
far?
I will
The
do.
addition of a row with one more ball than the last.
I'm going to
So
mute you,
far-
Richard, so you can continue to talk to yourself. I've already muted you, so go ahead. John, do you want to?
So far, we have a numerical progression.
There
N
we go.
squared minus n. Whoops, what happened there?
It's coming back. Okay, do you see it now?
Yep. So far, we have a numerical progression, n squared minus n in brackets over 2, that happens to be modelled by triangular clusters. We might have chosen to discuss a variety of other sequences. For example, the numbers generated by n squared, 1, 4, 9, 16, 25, which could be labelled square numbers because they are geometrically represented by square clusters. But we have a specific motivation for paying attention to triangular numbers because of one especially significant characteristic. The nth term is the number of relationships between n items for n equals 1, 2, 3, 4. For example, suppose that for any given number of people, we wish to know how many telephone lines are required to link everyone to everyone else by a private line. The answer is the triangular number corresponding to a number of rows, one less than the number of people. 2 people require only 1 line. 3 require 3. 4 require 6. And n over 2 private lines. It is no longer far-fetched to imagine applications for this formula. The real lesson from triangular numbers is that significant algebraic expressions, such as n squared minus n over 2, the number of relationships between n events, can be represented geometrically. That
Right.
much established, we proceed to the next development.
No. Okay, good. Any
Right,
comments or
that
questions? Go ahead.
That right there is her point. Thank you.
Well, that's one of her points. This is about the relationships point, but there's also a way to count in triangular numbers. There's a way to count the number of balls in the previous set. That's stacks of spherical, if we're counting oranges. But continue. This whole thing started out counting oranges, if you recall. Okay, good. Do you want to continue reading from Tetrahedra?
Yes, I will.
Yeah.
Tetrahedra. We can stack triangular arrays of decreasing size, creating tetrahedral clusters. We could thereby isolate a sequence of tetrahedral numbers, but let's go back to the very beginning. One sphere alone is completely free to move, and close packing is, of course, not an issue. Suppose we have 2 billiard balls tangent to each other. If the only requirement is that the 2 balls stay in contact, we shall observe that they are free to roll around each other's entire surfaces. We then introduce a 3rd ball, allowing it to roll in any direction while touching at least one of the first 2 balls. It eventually rolls into the valley between the other 2, establishing a naturally stable triangle. At this point, we require all 3 balls to stay in contact and discover that they are still able to roll.
It's there.
But only inward or outward, toward or away from the triangle center in tandem, like a rubber donut, to use Bucky's words. The freedom of motion of each sphere is thus considerably more limited, spinning about one specific horizontal axis instead of unrestrained motion in every direction.
So there's our examples of our balls.
2 balls, 3 balls, 4 balls. A 4th ball rolls across the surfaces and lands comfortably in the triangular nest. Suddenly, all 4 balls are locked into place, unable to roll or move in any direction. This is the first stable arrangement with the requisite minimum of 4. The tetrahedron is once again at the root of our investigation. At this point, it may be illuminating to construct some of these structures, for example, with styrofoam balls and toothpicks or small plastic beads and glue. One particularly satisfying demonstration involves bringing 4 spheres together and trying to create a square. It is easy to feel how unstable that arrangement is. The balls gravitate naturally toward the tight tetrahedral cluster. Fuller placed considerable emphasis on the benefits of hands-on construction to gain thorough familiarity. The theme of Fuller's tetrahedral sphere packings is the presence or absence of nuclei. The word nucleus evokes the image of a central ball spatially surrounded by other balls, which is exactly the way Fuller uses it for the VE packings. However, his observations about tetrahedral patterns are based on a somewhat different approach. Most of the impenetrability of the sphere packing sections in synergetics can be removed with one simple clarification. A nucleus in VE packings is defined as a ball at the geometrical center of the...
It's there. Should be there now.
Exact center of an individual planar layer. Start with the 4-ball tetrahedron.
Well, hang on. Let's pause right there. Before we start, we're at the time to end. So I'm going to go ahead and call our meeting.
Yes.
We have only a few minutes to go. I'm breathing deep. John, how are you feeling? And what are your
I found most of today confusing, and I found the friction disappointing. So I'm glad that I was able to join you again today, and I won't be here next week. I'm going to be away. So I wish you the best next week. Thanks.
Great. Glad to have you. Manu, how are you feeling? And what are your takeaways today?
I'm feeling disappointed. And when I'm disappointed, I like to say it because I cannot stand that a truth that is said, that is universally demonstrated, is perverted. What happened today is something that is, in my opinion, clearly said and demonstrated, and she said it at the end of the paragraph, and I read. The real lesson from triangular numbers is that it's significant algebraic expression, such as n squared minus n divided by 2, the number of relationship between n events, between n vertices, an event is a vertex, can be represented geometrically. That's the lesson. It is difficult to have a graphical description that you call, we used to call it in mathematics, either you have an extensive definition of something or a comprehensive definition of it. Algebra, the objective of it is to have a comprehensive definition. If it's possible, it makes life easier for everybody to step ahead and go. And that's it. To build these things is very difficult. You see all the time. This is an extensive definition of a three-frequency tetrahedron. To write it, knowing that the frequency is n-1, is easier. So that's what I get from you. Otherwise, I'm grateful. And I will get, I don't excuse, it's not an excuse, it's not an apology. I'll get very frustrated from time to time when I think that fundamental things are violated. Okay. Han, how do you feel? What do you take away?
Okay, I just, there's a reason why I come to these meetings, for enjoying, and I'm very grateful for that, and I don't think ever once have I been, disappointed, yeah, even with friction and all that, because through that friction, there's so much clarity that came out. Even today, as I was listening to both sides of it, not both sides, actually, they're all, this is part of the world, right? And the formula is the formula. I don't think any one of us is refuting the formula, right? Or formulate, because there are two here. So there's no refuting of those that universal principle, general principle, yeah. And the thing I really like about this group is we do talk about beyond what is irrefutable, right? And that's the power of this group, because and the books that we are reading every time we move into another book, the next book, and I'm seeing the same thing, because we're looking at both the world as it is. So you have the irrefutable part, and you have the part that is really open to interpretation. But the more importantly is that for the first time, I'm seeing science together. There's the physical and the metaphysical, or whatever the universal principles are, both the physical and the metaphysical. So even the physical side, I've been wowed by by understanding the patterns, right, appearing, whether it's to scale small, like microscopic, or beyond to being too big to be visible. So that is the physical part, right? And then there's also the metaphysical. So things like cosmometry, the book itself. I've been telling everybody about it, because I'm like, wow, they're talking about, we're talking about the, what do you call it, unified physics and ancient geometry, and then music, and then you have consciousness. They don't go together. I've never seen it anywhere where it's put together. Bucky, when he talks about any of all his books, he has concepts, he has truths, and also he pulls in the truth of the world written from his perspective, which actually sits across so many aspects of life, So it is for the first time discussing whatever information that's been presented to us in a very I think the word holistic is too overused, right? So I would use the word, and I'm not sure if I'm using it correctly either, but very multidimensional, right? People talk about interdimensional, interdisciplinary, but I think the world, and we have been working on the school, and we are quite comfortable with the word multidimensional for people to understand, because you're dealing with both the human side of people learning the world, together with whatever is delivered factually in books, right? But English is never factual. It's a lot of it is, not factual as a subject, right, to teach. When you go down the path of figurative language and describing it in ways that you feel, and so on and so forth. So that's why for me, this group and the books that we're doing is bringing all those into context, right? Like really, really pulling it together in a manner that I think more people should know about. Yeah. So even the music part, because just the other day I was having a discussion with people who are really from the music industry, and they play music, but they don't see the science and the math side. So it was a very interesting thing, because when we went down the path of talking about music, and music being the creative side of life, but no, I know music is part of the facts and the science of frequency, for instance, and it's the basis of light and sound, right? They're all on this. I know that's why I got out of it. Yeah. So for that alone, I know I will be here, okay, and not and I just want to be clear, never been disappointed, even when we go down the path where just now the arguing, because from the arguments I got clarity out of it for myself, okay, yeah. So Richard, how do you feel, and what is your takeaway?
Well, I feel I'm in a learning mode, and I have to start with what Manu concluded in terms of the counting of relationships, and that's what I have come to understand in terms of a formula. R, meaning relationships, R equals n squared minus n over 2. Now, what threw me off today in reading Amy on the page previous was that she said numbers can be counted in the same way. And so the formula that she had introduced to us on that other page was n equals n squared minus n over 2. And so all of a sudden I'm saying to myself, I understand r equals n squared minus 2. And now I have to try and understand how n equals n squared minus 2. And that's what I was talking to myself about. I was trying to work out that numbers formula so that it would resonate well with me and all of us. And so there's no question about the r equals n squared minus n.
Yes.
That is complete for me, and it has been for some time, having read it in Synergy and trying it out in practice. I use it all the time. So I'm still throwing off of n equals n squared minus n, and that's what I'm going to keep working on to try and understand. And I'm sorry that we got into the kind of friction we did, because it was a two-way where we're kind of missing each other in the sense of what we were struggling to understand. And Manu was trying to get us to understand r equals n squared minus n over 2. And we were trying to say, we understand that. But it's that other one that's still struggling. I'm still struggling with, and so I have to do some more work. And I, I actually want to hear more on how n equals n squared over whatever it is, n squared minus n over 2, that counts numbers kind of in the same way it counts relationships. That's my struggle, and that's what I'm still trying to work on. So in that sense, it's motivated me to keep trying to come to grips with the n numbers part of this formula. So so I thank everybody for the kind of dialogue that we've had. Sometimes it slips away from dialogue, but it still constitutes learning from each other. And so where are we? We've got, over to you, Steve. How are you feeling? What's your takeaway?
I think Joe hasn't gone yet.
Oh, Joe, right. Sorry, Joe.
Hey, everybody. So no, it was great to be on the call. I only caught the latter part of it, but it was a really fruitful discussion. I mean, the parts that I was listening to, I do think that this is it's beneficial, to both everybody trying to express their reading of the material itself. I very much appreciated Anne's distinctions again, where she brought it into a more, she related the metaphysical and the physical to reality. And as far as how relationships actually manifest themselves. So, I'm looking forward to going through this translation. Going through this chapter a little bit more deeply next week. In the past, when I have looked at the n-2 examples, and even the one that you pulled up here this evening, it has been about interrelationships. So that's been like a basic idea. So I being in the car, I wasn't able to see exactly what was the main point of discussion, but no, I really look forward to next week's discussion. I do appreciate the contribution of just getting back to the idea that it was 6 and how that actually relates to the formula itself. Anyway, Steve, I think Steve the only one.
3 squared.
Steve, you're muted.
Yeah. So thank you, Joe. Okay, so I will say, because I am conducting the call, that we've had a problem, Manu, because we have started a conversation where we posed a question, and then you come in at that perspective and are trying to explain what you see when you came in. There was a whole another conversation going on, and with love and kindness, I'm sharing that I saw something today that I think is going to answer Richard's question. And if you guys, I stuck in the comment over in the chat, I translated, because I thought that Amy's words were very unclear. And so I'm going to read for you my translation, the way it appears there. I also show her actual wording from page 124, 125, and I'm going to read it for you now. And I think, Richard, this will resolve your issues about n equals n squared, because it's not n, it's n when n is a set of triangular numbers. That's what the n is. And so it's when n is a set of triangular numbers. That's the solution. So here's how it reads. The formula n squared minus n over 2 might appear to be a more difficult way to obtain these values, that is, the number of balls in a triangular set of balls in the previous triangular set of balls. Remember, we were at 5. We used the formula for 5 to determine the number of balls that were in the set of 4, right? And then she continues and says, and certainly for small groups of balls, it is easier just to count the balls. But of course, for the 20th or even the 19th triangular set, or triangular number, or set, triangular set, it is far more direct just to use the 10, to subtract 10 from 10 squared and divide the number by 2 to get 45 balls in the triangular set, than to draw the rows and rows, 9 rows of circles or balls to determine the total number of balls in the set. So if n equals the number of balls in a triangular set, and you have 5 triangular sets in a 5 triangular set number, there you go. So instead of being n equals n squared minus n over 2, it's n when n is a triangular set of balls, or a triangular set of spheres closely packed. That's what the n is. And that's what Amy, as far as I can see, was trying to communicate. That, once again, I'm just going to be very clear, because anybody listening to this call, when she said, when we came to this point here, that if I want to know how many balls are in the previous set, I simply take the number of sets, put it through the formula n squared minus n over 2, and I will determine the number of balls that are in the previous set. This is independent of the interrelationships. If there are 20 balls, if I use the number, if I want to know if I'm trying to compute the number of balls in a set of 9 triangular set of balls, all I have to do is take 10. 10 squared is 100 minus 10 is 90 divided by 2 is 45. And bammo, I know how many balls are in the previous triangular set. I'm pretty sure, Richard, that resolves the problem.
Yeah,
And
actually, it says that very clearly. She said, she talked about the 10th row and then instead of drawing 9 rows.
right,
See, she's
exactly
talking about
right.
9 rows of the 10 rows.
That's exactly right. So when it comes down, she says right here, with the 20th or even the 19th triangular number, it's far more direct to use the formula to count the number of balls in the previous set. So it's interesting to note that, therefore, that the number of interrelationships of any nodes, that formula for determining the number of relationships with a set of nodes, is also the number for determining the total number of balls in the previous triangular set. That's the solution. And that's what I was striving at and going from there. And you don't agree, right, Manu? Okay. Well, you can read the words here and see if I'm wrong, and please read the words and tell me where I'm wrong. So I've got the words in the chat.
Say that finally, and I've written it in the comments so many times. That formula is the relationship between, or map the relationship between the number of nodes of any set and the number of independent relationship or interrelationship between those elements.
That's true.
Yes,
what you're saying is exactly true. And the
wait.
formula has another purpose as well. If you read Amy, it'll tell you that, and I've got the words right there. Please, Manu, just read it. You can disagree with me, my friend, but just don't tell me I'm wrong, and don't tell me there's only one definition.
Have I said so?
Have I said so? Please look at my words and tell me where I'm wrong with my words, my friend.
No, I don't. No, you are free to write the words that you will. I don't want to judge your words.
Well, then please, we're complete. You're going to repeat.
Okay, that's fine.
You were going to repeat yourself. No reason to repeat. I'm giving my takeaways.
Okay,
I think it's very important for everyone here to have their point of view. And I'm going to maintain my point of view. And I agree with your point of view, Manu. What you're saying is exactly correct.
I don't have a point of view, Steve. I read
well, you demonstrated more than a point of view tonight.
No, I didn't demonstrate anything. I just repeat what has been established from ancient times.
And I'm telling
we
you,
all know that.
If you are creative,
I'm telling what I've learned in this book, brand new, my friend. Okay,
That's
I'm
fine.
complete. Please don't argue with me. I'm sharing
No,
my share.
I'm not arguing with you. You asked me a question. I wanted to answer the question, and you stopped me. That's
The
fine.
question I asked you was, if you please read my words, and if you don't agree with my words, correct my words and tell me where I'm wrong.
I said, no, I don't want to correct your words.
Well, please, I'm inviting you to do it. And if you don't want to do it, that's fine with me. And
no, I don't want.
I share. Okay.
Yeah.
Good.
Steve,
I really don't want to correct
Manu's
your words.
answer. Yeah, he doesn't want to comment on it.
Well, it's too
Yes.
bad, Manu, because I'd love to get your opinion on the words that I came up with, which I think are an interpretation of Amy's words here and the point she was trying to make.
Well, if Amy is interpreting something and saying that, I dare say that she has to go and revise her interpretation.
Thank you, Manu, for your point of view.
That's it.
And so we'll see you all next week, or whenever you can make it. John says he won't be here next week, but we'll see how we go from there.
Good.
Thank you. Good night.
Good night,
Bye.
everyone.
With love and compassion.
All right.